All right. Hi. Thank you for coming to this talk. I think it's one of the last talks of the night or of the evening, and we'll get some beers afterwards, which is always exciting. My name is Tuomas Artman. I'm a mobile engineer on the mobile platform team at Uber. My home base is San Francisco, but I'm essentially here to help the Amsterdam office and the engineering office over there with this conference, and I thought it would be a good idea to try to give a talk at the same time to you guys. I'm going to talk to you about essentially our new RIB architecture that we have created over the past 1.5 years. I want to talk about the motivation why we actually created a new mobile architecture. MVC, MVV, and MVP are pretty good architectures to begin with, but we started to stumble into problems as our engineering base grew. I want to talk to you about sort of the motivation of that decision, how we came to that decision, the process that we went through, and in the end, I want to talk about the architecture itself, give you sort of an overview of what we built and how it works. We open sourced the RIBs architecture, or the architecture framework, a week ago, and we've been the #1 trending Java repo on GitHub for the full week, except for today, where we dropped to #3. So hopefully we can change that today by having you all give us a star at some point. Going into why we built a new architecture, we sort of have to step back a bit and talk about the history of Uber as well. I'm just going to glance through this rapidly. I know that's not very engaging for a technical audience. But 5 years ago, this was the entire mobile team that Uber had. 3 people, I think 2 iOS engineers and 1 Android engineer, working super hard on offsite, creating the first application, or the second version of the application that was to be the Uber Rider application. Since then, myself, I joined 3.5 years ago, and we had 15 engineers working on mobile at that time. And in those 3.5 years, we've grown to 400 mobile engineers, essentially working on 2 primary or 3 primary applications, and then some smaller ones as well. So what we built what the guys in the picture built was essentially this application. I don't know if you've used Uber 2 years ago. If you have, you probably remember this application. A year ago, we launched a new Rider application, which was a full rewrite of what we had, and we'll get into why we did a full rewrite, because usually that's not the most sane thing to do when you have a growing business. This was the application. It worked fine for a number of years. It was essentially your vanilla MVC architecture, and we started having problems. Around the time I joined 3.5 years ago, there were already problems to be seen that maybe MVC doesn't work at our speed, even only with 15 engineers. We started having problems where multiple teams were creating functionality and features in the mobile application. In one place where all the integration happened, you had to test multiple paths from multiple teams in order to make sure that your application worked. And me, for example, my first project that I did was the destination entry on this application. I do remember that I counted 23 different code paths that I had to manually go through to make sure that the application worked, because we weren't super keen on having unit tests or UI tests back in the days, because we were moving so fast. So it was pretty overwhelming to develop new features on this, and it was becoming slower and slower as we started growing. I just joined when we started to have the hypergrowth phase, and essentially a year later we were already at 100 engineers working purely on mobile. At the same time, we started to have problems with the design itself, or the design rails that we had in our application. And this is an actual screenshot on the right of an application, and the user is in Chicago. If you look at the bottom tile down there, that's all the products that are available in Chicago. And when the designers designed the application, they figured we maybe have like 3 or 4 of them, but the city teams wanted to put in more and more products, and it became like this. At the same time, the map area grew all the time smaller and smaller, because feature teams wanted to have their own functionality in there. They wanted to put in banners, for example, the pool banner that you see, share your ride, split the costs, was something that the pool team put in to promote their feature. And we didn't really have good guidelines on on how new features should be, should be put into the shared space that every team integrated with. So we ended up with quite a few examples of pretty bad UI where you had multiple of these banners layered on top of each other, and you barely could see the map because of that. And 1.5 years ago, the design team came in and said, we probably have to redesign the whole application in order to be successful years from now, and in order to come up with a design framework that would allow us to build an application that not only supports the status quo that we have, but years to come from now. And we started seeing ourselves in a situation where we had an old application that had a pretty big code base, and we had a lot of engineers, so we could technically go through a rewrite, but everybody was super concerned. Rewrites usually sound super bad. You don't really want to go into them if you're not absolutely have to. I guess many of you already have experiences from rewrites going wrong, and instead of 3 months taking 3 years. And we didn't take that decision lightly either. We spent essentially a year trying to migrate, trying to change the existing architecture, put in better state machining in order to help our engineers to move at the speed at which they wanted to move at. But in the end, when we saw the new redesign, we looked at it and we were like, this is going to eventually change how the application is built. And every single feature, at least on the view side, needs to be rewritten. And because we didn't have a very coherent architecture at that point, that also meant that business logic would have to be rewritten at the same time. So we decided that we should do a full rewrite. And again, we didn't take that lightly. I think at that point we were privately valuated at $70 billion as a company already, and this was essentially bringing in all the revenue. So we really thought about it for a while before jumping into it. So the next step is when you want to re-architect your application, when you want to put in an architecture that supports large teams, because that was really our problem, having hundreds of engineers every single day committing code to the same code base, and sort of keeping them somehow not clashing into each other. We needed to come up with something, and we started with, well, if you're going to do a full rewrite, why not take the time and figure out what you want from that rewrite, what you'd want from a architecture. And we came up with 6 goals that we wanted from our new architecture. The first one was 4 nines of reliability. And it doesn't sound like a thing that an architecture would really help you with. But we found ways of making that reliability be helped with the architecture choices that we made. Reliability is not only crash-free rates, it's everything else. Like if a user can't, for some reason, complete a flow or a funnel, that essentially means that the user couldn't take a ride, which means we failed. The application didn't crash, but it still didn't work. So 4 nines of reliability was important for us, and we wanted to make the architecture work for that. We also wanted to do this once and not have to come back 3 years from now and do a second rewrite. So we wanted to support Uber's growth for the next years, whether that be 800 or 1,000 engineers working on the same application. We wanted to provide rails for both design and code, hugely important to be able to say, here's how you should code in this new architecture, in this new application. Here's how you should design for this new application. You saw the problems that we had in design before because we didn't have guidelines or rails for designers. And we wanted to make sure that they would be able to come in, still have their freedom within a certain context to design the feature as they wished, but still conform to a certain set of guidelines in order to not stray from the overall user experience. We wanted to put monitoring in as a first-class citizen as well, something that the architecture can help you with. If you can't test if you can't monitor your application, then it might as well not exist. Like, you don't know what it's doing, you don't know if it's running, you don't know how many users are using it, you don't know if users are successfully completing certain flows. So we wanted to make sure that the architecture would automatically give every single team monitoring for free out of the box. We wanted to de-risk experimentation as well. Whenever we put in new features and functionalities, we do an A/B test. Nothing really goes in without experimentation. We want to make sure that a feature that we put in actually hits the bottom line and makes an impact somehow. And finally, we wanted to also make magic. We want to make sure that the architecture would be able to create an application that was whose performance was second to none and that would gracefully degrade as well when you went to low networking conditions or low-end devices. So these were the 4 architecture goals that we set out to accomplish. Maybe a 7th one that we added sort of later was that we wanted really both of our mobile engineering teams, iOS engineers and Android engineers, to really work on the same kind of code base, to work on the same kind of architecture, to be able to create functionality and features together and not having to sort of spend twice the amount in figuring out how something should be implemented. We have a process called RFCing, requesting for comments throughout the company. Whenever we put out a feature, the engineering teams will send out a document detailing how they're going to implement that functionality. And previously, you would always have an iOS RFC and you would have an Android RFC. And we wanted to make sure that you didn't have to do 2 different documents, implementation documents, but that we could talk with the same terms, we could use the same class names, we could use the same terminology, and that implementation details when it came to UI, surely you had to differ between iOS and Android, but maybe on the business layer side and how you implement that feature, only one explanation was necessary. So you could essentially double the effectiveness of your mobile teams when they were designing a feature. So how did we do this? We started in January 16, and we launched in November with a new application. And this was a full rewrite of everything from start to finish. We started with a pretty small team, because we didn't want to tell anybody to stop working on the existing app. We were still a growing company and still are, and we didn't want to pull the feature teams out of their daily work. They wanted to make the existing application better, and we let them. So we said, let's spend half a year trying to figure out how Uber should be building applications. Let's do that somewhat in isolation, without getting too much input from others. Maybe in hindsight that was a bit of a problem. We should have more actively sort of engaged the entire company to take part in designing the architecture, or at least being able to give some input. But we had a team of 8 people, 4 Android engineers, 4 iOS engineers, working for 6 months, trying out everything. So we started with MVC. Can we make MVC better? Nope. Can we do MVVM? Can we do MVP? We had a take on Viper. And we built out core flows for all of these different architectures. And we tried whether it would work for us or not. And in the end, we came up with, no, it won't work. Like the problem is that all of these architectures are based around the view. When you base things around the view, everybody has to integrate in one point. And that becomes a mess at the scale that we had. So we decided that it's time to write our own architecture. And we started to build out what now is called RIBs. And 6 months in, we were pretty happy with what we had. We had done that in isolation. We were writing super ugly-looking core flow features where you could take an UberX trip and actually have a working application. And we invited the first team, the core flow team, to join us in this rewrite. 20 engineers from the core flow team jumped on board and started porting actual designs and actual functionality over to the architecture. And at that point, we realized that we hadn't really taken everything into account. We had missed quite a few points. For example, complicated animations that we had taken no take on at all. We missed that people would want to somehow manage multiple views and coordinate their animations together. And the current architecture that we had wasn't really suitable for that. So we made changes to the architecture, working together with that first team. And 2 months later, we thought that we were were there, that we had a good architecture that would scale for all of our teams, that would give us all the goals that we wanted in the beginning, and we essentially opened it up to everybody else. We went to all the other teams and said, you can now port your functionality over. And they did. Some teams started immediately because they knew that it would take them 3 months to switch everything over. Some teams didn't bother. They still continued experimenting on the old application, and just in the last few weeks ported their functionality over. But in the end, we launched in November, and the launch went pretty successfully. We had some problems, obviously, because it was a full rerun, full redesign, some things that we didn't anticipate in some countries. But overall, we met the reliability goals pretty early on. By having rewritten everything, we were close to 4 nines of reliability on the mobile application. So where we are today is a writer application that has 2 million lines of Java code, 1 million lines of Swift code, which should sound pretty big to everybody. It sounds super scary to me whenever I see this. This obviously includes unit tests and UI tests, so this is not all production code that runs in the mobile application, but it is a lot of code, it is a lot of teams. The code base is huge. We support the application in, 68 countries or so, with different feature sets in multiple cities. So in the end, what we ended up building was essentially 2 things. We built the core architecture, which we now call RIPS architecture, and on top of that, we built the application framework in order to support the Uber-specific use case. On the RIPS architecture, we made sure that we had things like dependency management, reactive data flows, testability, compartmentalization, scoping. Because that wasn't enough, we had to integrate things like monitoring and analytics that would integrate with our backend systems at Uber on top of the architecture. The RIPS architecture is the one that we've open sourced. If you want to use it at some point, if you give it a try, you probably have to build something on top of it as well. It will be a basis or a starting point for you to start using an architecture that scales for big engineering teams. And the application framework is something that we might be looking into open sourcing at least pieces of it, for example, the plugin management, some point in the future. So what does RIPS stand for? RIPS stands for router, interactor, builder, and an optional presenter and view. These are the core building blocks of a RIB, and a RIB is a core building block of the application. We will jump into what these all mean later in this talk, but for now, know that there's a thing called RIB, which has 5 different pieces within it, and they're called a RIB. The one thing that we wanted to solve really with this architecture, and we found 2 big problems that none of the other architectures would be able to solve, was the massive view controller problem or fragment problem. If you go to iOS, the joke stands that MVC stands for massive view controller. On the Android side, our fragments were huge as well. If you go into the request flow, which is essentially the first screen that you see, where the user can then start, taking products, putting in GPS location, searching for location, that was 5,000, 6,000 line of code, all essentially integration code, and super hard to maintain, written by 200 engineers. So nobody really had a good take on that. The other problem that we had was really convoluted state machines. This is an actual screenshot of our state machine that we implemented for the request flow on the old writer application, where essentially you could hit request, you could confirm your location, you could select a product. There were some other views in between as well, and all the lines are transitions from one state to another. And when you have transitions like these, it essentially means that every single one of these state pieces or things needs to know about the next one they're going to, because they need to handle some sort of animation. And we looked at these 2 problems, and it turned out that we had a common solution for both of them. And that was a state tree. We thought to ourselves, wouldn't it be awesome if you could just design the state of our application, our entire application, as a tree? And if you're now shaking your head, that's exactly the same thing that we did. We initially threw this idea off because mobile applications are inherently integrated. You've got, awesome views that animate, that morph into one another, where you really need a state machine that you saw on the previous slide. But we still looked into this. We continued down this route, and in the end, we found out that yes, it's possible. It is possible to take any application and model its state as a tree. Some of these nodes could have multiple children active at the same time. Some of them will have none. But in the end, you could model every single application. At least we haven't found an application that you couldn't model with this very nicely. So this is an example of a very simplified model of the writer application. You've got a root rib, whose responsibility really is to figure out whether the user is logged in or not. You've got a logged-in rib, which gets attached when the user logs in, a logged-out rib when the user is not logged in, and there are things like the menu, the on-trip thing, the location editor, the favorites. Let's look at the decisions that a rib does. Here in the case of root, we wanted to make sure that in ribs, everything is as compartmentalized as possible, that all these business logic units make the smallest amount of business logic and the smallest amount of decisions possible. So every single node in here doesn't know anything about anybody else. It knows that it has a child. It doesn't know what happens in that child. And it makes a local decision to move the state tree forward or backward. In this case, when the root rib initializes, the interactor, which is essentially the piece that drives the business logic, makes one decision, and one decision only, throughout the entire application. Do I have a user token or don't I have a user token? If I don't have a user token, attach the logged out rib. If I have a user token, or if I get at some point a user token, remove the logged out rib and put in the logged in rib. That's all it does. And at that point, nobody else in the application will ever need to have to handle user tokens or authentication or any of that. It's handled up in the top. If you're attached on one side, you know that you're logged in. If you're attached on the other side, you know that you're logged out. So the logged out rib gets attached. Now, its rib will do probably something more complicated. It will have a user form where the user can enter its credentials, press a login button, go back to the interactor. The interactor will send up a network request. And somehow, and I'll show that later in a slide, how we pulled this together, this backend request that is sent by the logged out rib comes back and is applied to the data state of our application, and the root rib is informed that there's now a token. So because the root rib, again, has only one decision to make, do I have a token, don't I have a token, it now got a token. So what it does, it attaches the logged in rib, and it detaches the logged out rib. And everything else in this state tree makes similar, very simple assumptions. For example, the logged in rib, again, you see it has 3 children, it has request, menu, and on-trip. As it so happens, the menu rib is always attached. There's no business logic associated with it. But the request rib and the on-trip rib are mutually exclusive. So the logged in rib, again, looks at the state of the application and sees whether we are on a trip or whether we are not on a trip. If we are on a trip, we attach the on-trip rib. If you're not on a trip, we attach the request rib. And thus, the application moves forward. If at any given point in time, our data state changes and we get a trip object, the logged-in rib will, again, utilize or execute its business logic. It will remove the request rib associated with all the views, and it will attach the on-trip rib. This state is also inherently business logic driven. All of these ribs are essentially business logic units to this point. We haven't talked about views at all. Every single rib can come with its views, but the big differentiation between ribs and other architectures is that we route or we have business logic at the core of the application and the architecture, not view logic. Views follow the business logic, not the other way around. Some of these ribs are highlighted in green, meaning that they come with their views. Some ribs might not have views at all. And to give you an example of what that means in terms of the application, you've got the menu, which is associated attached up at the top left. You've got the location editor, which is at the top, and you've got the shortcuts down here. One other thing to notice is how this separates all the pieces nicely. Because a rib doesn't know to which parent it is attached to, it only knows what children it has attached to itself. It has to live in a world of its own. So if you take, for example, the location editor rib, it doesn't know where it is. It has been assigned to a certain area on the view by the parent. So when the request rib attached the location editor rib, it said, you can draw here. And it has been given an area to draw in, and the location editor draws in that area. If it's being moved around, it really doesn't care. If it's being resized, it will probably re-render itself. But it knows nothing about the world outside of itself. So you can really go into the code of the location editor and you can live in your own world. You don't have to go outside. You don't have to go upwards. You make modifications, and those modifications will only affect logic re-rendering of the location editor. And the same applies to everything else. We could move the location editor to other ribs as well. Like we can reuse them and just listen in on what they provide to their listeners. So the attachment between, or the result passing between these ribs happens through listeners. When you create a rib, you pass in a listener interface that is essentially used to deliver results from the location editor. In the location editor, it's super simple. The location editor at some point will say, the user selected their location. And at that point, it's up to the parent to do something with that information. To show a quick demo of how this looks like, I have to, unfortunately, use an iOS simulator, because we don't have this functionality ready on Android yet. And we're going to just launch the application. In debug mode, it will have a small local web server that we can use to have an application running that will inspect sort of the logs that get triggered by our automatic logging. And we have this small website that will render the rib tree as it happens and as it moves around. So this is the initial rib tree of our application that just got launched. We start off with, I don't know if this is visible, root router, main router, writer router, request router, home router, feed router, and so on and so forth. So let's drill into the view, in the feed. The feed is down here. When I move it up, you see that new riblets are created. And they're created while I scroll up. And this is pretty useful information to sort of be able to debug things. I can see what gets attached. I can sort of get a good understanding of what has been built in this rib. And I can use it for debug purposes. For example, if I move all of this down, I still see that they're attached, which is probably something that we shouldn't do. Like we're consuming unnecessary memory here, and we should probably clear out these pieces. Same if you go into the location editor, something big happens. We switch entire ribs into a new section of the application. If we go back, we switch it back. If we select a certain location, we get a request router that gets attached to the right router, and all kinds of other riblets that get associated with it. And again, if I somewhere in here create a location, I get the same location editor, but now attached to the request router. And yeah, so this has been working for us pretty well. And even though we have a lot of animations that get synchronized all over, everything moves smoothly into one another, we still haven't found a case where modeling your logic state as a tree in a mobile application would not work. And really the benefits that you get out of it is that you can now compartmentalize all the pieces of your application. You can hand it off to different engineers. Engineers will create a feature, and nobody else will know that that feature exists. It will be attached somewhere, and that's all sort of the knowledge that ribs have of each other. They know that they have to create one, they have to attach it, they have to maybe pass in a listener to inspect the events that come out of that rib, but that's the interaction and integration you can do between ribs. And it's actually enforced. You can't do more. You can't go in and grab something out of that rib. That interface for that listener is the only thing that you can use. And that enforcement has worked pretty well for us. So going back into the state tree, it happens so that dependency injection works beautifully with this tree as well. We have a thing that we call dependency scopes. We have an entire talk on this. I can point you to links later. But let's look at an example. Let's say we have the access token. And the access token is used by multiple ribs throughout the application. Because whenever you make a network request, essentially you need to have access to an access token. Otherwise, you can't call the service. So in this case, the root creates that access token. We call it dynamic dependency that we then hand down selectively to one of our children. The root will never hand that access token down to the logged out rib. So the logged out rib never can get an access token, which essentially means that if you try to move some of these ribs to the other side, your compiler won't let you because that dependency cannot be fulfilled. So if you take the favorites, move it up to onboarding, no go, compiler will say, I don't have an access token, I can't fetch it from the dependency graph, so you can't add me here. It can be moved downwards, so logged in obviously gets that access token, and it again can decide where to move it. Usually we allow pretty much anything except for maybe some mutable classes or mutable streams that we have. Anybody who wants it, when it's created, can take it. So everybody underneath that first dynamic dependency can get access to that access token. If you then, for example, are in the logged-in rib and we are on trip, that trip object that we received from the service essentially says where we are, what we're doing, who our driver is. That is received by the logged-in rib. And the logged-in rib will pass it down to the on-trip rib. So the on-trip rib at this point is attached, and the trip object is passed down. And anybody who's attached to that on-trip, underneath on-trip, will be able to read that trip object as well. And if we, for some reason, complete the trip, again, the logged-in rib will create a new trip request object, which then can be fulfilled and filled out by all of the other ribs that are associated with the tree that goes into request. So let's dive into the internals of a rib. We just saw the state tree, which essentially is the overview of how you built the application, and that's maybe even the biggest point of what we did with ribs, because that makes it possible to build big applications and have huge engineering teams working on a single app and still compartmentalize things in a way that your engineering team can be effective. So we start off with the interactor. The interactor essentially is the brain of your application, of your rib. It drives all the business logic. There are other architectures that call it interactor as well. So essentially it doesn't know anything about the view. It just takes in streams or objects, makes some decisions, runs some business logic, and then decides whether we should go further in the application somewhere or somewhere else. It can also make network requests if it wants to get some more information, if it wants to, search for a location. That is the thing that does and drives all that business logic. The router is pulled out of that interactor, and while the interactor makes the decision on when to go somewhere else in the tree, the router knows how to. We could, and we've been talking about sort of moving the router into the interactor, but for now we want to keep it outside to compartmentalize a rib as well, and to remove the amount of code that we have in one interactor. So the router will be called into by the interactor. The interactor will tell it to go to the logged-in rib, and the router will be able to build the next rib and attach its views, and hand control over to that next rib. We've got the builder, which is the essentially most stupid part of the entire rib. It just builds the whole thing. Usually we don't even need to unit test it because building is mundane. It's essentially, unfortunately, boilerplate code. It builds everything, passes in the dependencies, and off you go. If you have a problem there, usually your compiler will tell you, and there's no unit testing necessary. And then we've got the two optional components, which are the view controller on iOS and the optional presenter. If you have a more complicated view that really would use a view model where the data that you get from the interactor isn't really formatted to be presented, usually use a presenter to create a view model to then call into the view and set its attributes. And the view controller is super dumb as well. It just has all the views, puts them in a place, and then waits for somebody to call in and set properties on those views, set label texts or putting colors or whatnot. So these are the 5 pieces. The most important ones are the interactor, the builder, and the router. Hence, we call it ribs. And you can have a view controller and optional presenter. And here's a diagram of how we use it. Like, this goes a bit beyond what ribs itself is, but I added it because it sort of gives you a good overview of how the events flow within a rib. So if you start off with an interactor, and let's be in the logged-in rib, for example. The interactor will give any data model to the presenter. In the case of a logged-in rib, there's probably not much data to give. Maybe there's, I don't know, the time that currently is if you want to present it somewhere on a screen. The presenter will create a view model and then call into the view to set these labels. The view in this case probably would be 2 input fields and a next button. When the user fills these in and the next button is pressed, the view will call into the presenter and tell it what just happened. It will say, I clicked this button. It won't indicate intent. The presenter's responsibility is to change that UI event that happened into an intent. So the presenter will say, aha, we clicked this button on this view. That means the user probably wants to log in. In order to log in, let me read that username and password from those 2 text input fields. And let me then call into the presenter, into the interactor saying, interactor, please log in with this username and this password. The interactor will take this request, might run some business logic, be like, can this user log in? Yes, this user can log in because the username is more than 3 characters and whatnot. So let's make a service call. And that's when we move outside of the rib. We probably have some networking component injected into ourselves. And we call into the service saying, please log the user in with that rib. And what will happen? The service will go into the backend. The backend will resolve that, give an access token if the user is actually there. The important part here is to note that we will actually, at this point, not receive any response in the logged-in rib. Because we want to manage states in a way where we cannot break it. So we've said in our application framework that whenever you make calls to a backend service that change the state of your application, you can make that request, but you will just receive an OK if it succeeded. You will never receive the data back. Because if you receive the data back, you could mess around with it. You could get out of sync in your application. Instead, we say any service endpoint that is being called that changes state in any way has to be registered globally with a handler pointing to a stream, and we use Rx streams for this, that will receive that data. In this case, there would be a writer stream whose user would be filled out with probably a username and access token. And that stream is accessible by the root rib. And the root rib would be listening in on those state changes on that stream and then make the decision to move forward to the logged-in rib. So that's how we model our applications. Like, what about the other architectures? The biggest thing that I can tell you is it'll probably work nicely for you. Like, there's nothing wrong with other architectures. If you at some point get into a state where you think of growing your engineering resources or looking at hypergrowth, then you probably want to look early into making sure that your architecture actually supports growing your engineering team, and have a look at ribs, because it would work for you at that point. So the biggest problems that we see in all of these, MVC, MVVM, MVP, and Viper, is essentially, that the view is at the center of everything, and you can't really break it apart easily. And it's sort of your view and business logic are locked together. And obviously, you get the massive view controller in MVC and MVVM. We do have a few. Sorry, I was on the next slide already. So what did RIBs give us? If you look at the router application today, remember we had 1 million lines of code on iOS and 2 million lines of code on Android. We broke the entire router application into about 600 RIBs. That's how many we have today. Many of them are reused throughout the application. You can just plug them in somewhere else. If the interface matches, it just goes in nicely. That means interface both ways. It needs some dependencies, and it will want to talk back to its parent. So if both interfaces match, you can just move things around as you please. Most of the RIB classes have under 300 lines of code, and this was a super important metric for us. We wanted to be sure that you can go into anybody's code, have a look, and in in a good amount of time understand what the thing is doing. And if all of your classes are under 300 lines of code, that's pretty neat. Obviously, we do have very complicated ones as well that go to 1,000 lines of code, but most of them are under 300 lines of code. All of the business logic is very, very well tested. We started with the router application 5 years ago that wasn't tested at all, and now we have almost full test coverage for all the business logic that is important. Again, the architecture helped us by putting interfaces in between every single component. Some say it's a bit heavy, and the biggest complaint that we've gotten from our engineering teams is that there's a lot of boilerplate when you use RIBs, because every single interaction between, for example, an interactor and a presenter, or an interactor and a router, goes through an interface, because that makes the code testable. But you get the benefit of having well-tested code. We also asked our engineers what they thought of the architecture, and we had massive increases in NPS. NPS stands for Net Promoter Score, essentially a measure of how willing a person would be to promote a certain architecture or a certain thing. And we had absolutely huge increases in this. So our engineers seem to like it, and we seem to be able to land commits very fast as well. We do have a few resources. There's a GitHub repo, obviously, for RIBs. And if you have a computer with you, I'd ask you to go in there and give us a star, because we want to get back to the #1 trending repo in Java. Nobody has a computer? All right, don't give us a star. We have a few video resources. If you want to, I would suggest you look at dependency hierarchies, because I only glanced over those. We've got like 20-minute talks on each of these at these URLs. We're talking about RIBs in general as well. And a very interesting talk is about plugins as well. So we use the RIB architecture to pluginize all of our application. Essentially, all of our features that are not core are plugins, which can be turned off by the server side. And we have guarantees in place that we can turn off all the plugins and all the optional features so that a user can take a trip, which is important in a mobile application, because when you launch a mobile application, when you send it to the app stores, there's no going back. You're sort of stuck with that version forever. So it's important that you can turn things off. For example, our map is a plugin. You can turn off the map, and you can still take a ride without the map, or scheduled rides, or most of our products are just plugins that we can turn off in case something goes wrong. And that is really my talk. Thanks so much for listening. We have a booth downstairs. I'll be at the booth drinking a few beers. If you have questions, you can find me there afterwards. Thanks.